Now, just as we did for centroids, where we did the integrals, and then we also had this method of finding ones for composite bodies. So breaking things down into shapes and then analyzing those shapes in a table to find your centroid, we go through that exact same process with moment of inertia. So we've been doing moment of inertia by doing all of these integrals, but we can also find moment of inertia by doing composite bodies. And this is really super useful, especially when we're looking at like the cross section of a beam or something like that. Something where in the real world we are looking at this cross section, it's usually made up of other shapes. For example, if we think of like an I-beam is a common example, right? An I-beam is just three rectangles that are stacked together on top of each other. And so we can break those down into their rectangles and find the moment of inertia for this shape. So this is what we're going to be doing with these moment of inertia for composite bodies, right? So just like in centroids, when we had some, say, shape like this, some trapezoid, and we said, okay, let's break this down into two different shapes so we can find the moment of inertia of the triangle portion and then of the square portion. So this is what we're going to be doing. But for this case, we have to use parallel axis theorem. There's no other option. You can only use parallel axis theorem for these shapes. And the way we're going to do that is using this basic equation. This is the one that we had seen before, but now without any integrals at all. We don't need to evaluate this as integrals. We're just using the standard form of the equation. Right, so moment of inertia about y, centroidal moment of inertia, plus a dx squared. So we're going to approach this a lot like we did with centroids, where we're going to have a table where we break everything down into a shape, and then each component within the parallel axis theorem equations here are going to be within our table, right? So our Ix bar that we pull off of the table, we pull our equation for this off of the table and then do the calculation. Our area, our dy term, and our a dy squared, so that we can just sum these down the table and then add them together, and that will give us our moment of inertia for all of the separate shapes together into one composite body. Let's take a look at an example. This example asks us to find the moment of inertia about the x-axis for this composite body shown. And so we're going to follow a very similar process to what we did with centroids when we were doing composite bodies, and that's breaking this thing down into shapes and then setting up a table with all of the ingredients that we need so we can add down the columns to solve this problem, to solve the equation, right? So since we're finding the moment of inertia about the x-axis, we're going to use our moment of inertia x equals the centroidal moment of inertia plus a dy squared, right? We have to use our parallel axis theorem. And so those are all of the little ingredients of information that we're going to be pulling out from each shape. So let's break down our shapes here. Again, there's a few different ways that you can break down these shapes, but I'm going to pick the one that makes the most sense to me, and it's okay if your breakdown ends up a little bit different. You should still end up with the same result either way. So for my first shape, I see a square here, this 200 by 300 square that is filled in. This is 300 by 200. I see this void in the center, this circular void, nothing in there. So again, this is a void, so it's going to be a subtraction, right? We're going to be subtracting out that area. The void, nothing in it, tells us it has a radius of 75 millimeters, all of our units in millimeters here. And then finally, I see this triangle over to the right side that has a height of 300 and a base of 150. and that is solid filled in. I've got 3 shapes that I'm going to be adding to my table. All these 1, 2, 3. So we'll set it up just like we did with the centroids. Shape, and then every piece of information that we need. So this Ix prime that comes from the table, the area, dy, and then the multiplication across, because this is what's getting added, a times dy squared. So that way I have both terms that are actually going in the equation located in my table. I'll do that multiplication across. Shape 1, shape 2, shape 3. Alright, so there's my table. And let's go ahead and start filling things in. So for my rectangular shape, my moment of inertia about the x-axis for that comes from the table. Again, it's 1/12 b times h cubed, right? So general equation 1/12 bh cubed. So my base in this case is 200 and my height is 300. So 1/12 times 200 times 300 cubed. I'm going to get a huge number in here. And I will use the scientific notation to condense this a little bit. So 4.5 times 10 to the 8th is what I get when I plug that into my calculator. 4.5 times 10 to the 8th. Let's go ahead and pull the moment of inertia of all my shapes here. Right, if I look at my next one down, my circular void is going to have a negative centroidal moment of inertia. It's going to be negative. Everything in this will be a negative for a void. So my area is negative, and my moment of inertia about the centroid x-axis is also a negative. So in this case, I'll go to my table and look up what the x moment of inertia of a circle is. And I see that it is negative 1/4 pi r to the 4th power. All right, so I'm going to plug in my 75 into that equation because it gave me an r of 75. So 1/4 pi times 75 to the 4th. Punch that into my calculator, and I get negative 2.49 times 10 to the 7th. And then finally, I'll do my pull from my table for my triangle here, which is 1/36 base times height cubed, which that makes sense. It's like 1/3 of the square value. Right, so 1/36 base of 150 times a height of 300 cubed. Punch that into my calculator. And I get 1.13 times 10 to the 8th. Right, so all of those values came from the shape itself and then looking up that shape in the table of standard centroidal moment of inertias. So those all came from looking those up, plugging them in. Now I'll do my areas, which are going to be even simpler, right? I can just look at the shape and I know what my area equations are way back from geometry, right? Area of my rectangle is going to be my base times height, so 300 times 200. 300 times 200 gives me 60,000. 60,000. Area of a circle, that is pi r squared, but remember this is a void, it's something we're taking out, it's not actually there, so it's going to be negative. So negative pi r squared, negative 75 squared gives me negative 17672, right around there. And then finally for my triangle, area of a triangle is 1/2 base times height. So 1/2 300 times 150 gives me 22500 for the area of my rectangle. Those are easy enough. Probably the most difficult thing that you're going to have to pull out of these is your centroid locations, right? This dy. So this dy location, again, is your distance from the axis of interest to the centroid of each shape. So your axis of interest, in this case, is our x-axis. And then we need to find where the y-bar is for each shape. Right? Where is the centroid for each shape? Now, for our square and circle, they're pretty easy because they actually have the same centroid, right? They have the same center point for this rectangle and this circle, which it tells us we can read right off the side is at this 150 mark. So my dy in this case is 150 for both the square, the rectangle, and for my circle. Then I need to find my y-bar for my triangle. And we know the centroid of a triangle is always going to be 1/3 up from the longest side. Right? So my y-bar here is 1/3 of the way through. So 1/3 of 300 is 100. So this gets a little more complicated if you're not doing this from the x-axis or the y-axis, or it's offset some from your axis. So you'll have to be really careful about pulling these centroid values. This dy term is the one that will trip you up the most. So be really careful about this term and where you're pulling what you're getting there. Finally, our last one is just going to be the multiplication of a times dy squared. Right, so we just punch this into our calculator of our 60,000 times 150 squared, and I'm going to get 1.35 times 10 to the 9th. And then I just go on down. I've got my negative 17,672 times 150 squared, negative 3.98 times 10 to the 8th. And then finally, this 22,500 times 100 squared is 2.25 times 10 to the 8th. So my very last step is just to add these down the columns, right? The columns that I need are just my first and last column, because those are my first term and my second term in my equation. So I just need to add everything in the first column, everything in the last column, and then add those together. So when I add all of my xi, my centroid moment of inertia terms, I get, let's put this up here, I get 5.38 times 10 to the 8th. And then when I do my dy, a dy squared terms, add all of those together down the row here. Add just all down the line. Plus 1.17 times 10 to the 9th. And then I just punch those in my calculator, add those together to get what my final value is, and I get, I'm all out of room. I have no idea where to put this. Okay, I'll put it over here. Moment of inertia is going to be 1.72 times 10 to the 9th. Again, always units, millimeters to the 4th. Millimeters to the 4th, and that's our final answer. That's our moment of inertia about the x-axis for this body shown. But again, I've mentioned that you're not always going to be taking this about the x-axis or the y-axis, or maybe offset in some way. So let's take a look at this same shape, but instead of it asking you to take it about the x-axis, now it asks you to take it about the centroidal x-axis. So what it's asking you is, if I want to take the moment of inertia about the centroid, right, the centroidal x-axis, so wherever the centroid is, right, creating a new axis called x prime. This is why we see this x prime term. It's the centroidal x-axis. X prime, which has a value of the y bar of y centroid. So we're going to look at this same problem, but now with a different x centroid. In this case, what this means is that my dy term is going to be different, right? Because this whole time we've been saying that my dy is the distance from the x-axis to the centroid, but now it's the distance from the centroidal axis to the centroid of each shape. So if my centroidal axis is in yellow here, now my dy would be this distance, let's say for the circle, from the center of the circle to my centroidal axis is now my dy term. Right, so the dy term is changed even though my moment of inertia about the centroid here and my area are going to be the exact same. I'll also have to find what the centroidal axis is, so I'm going to have to go through and do the calculation to find what the centroid is so that I can find dy. So let's go ahead and clear this out and find our centroid, and then plug in our new dy values to find the moment of inertia about the centroidal x-axis. Now, from the last problem to this problem, we can move a lot of the same information over. For example, our moment of inertia about the centroid is going to be the same, right? So this is a property of the geometry. This is going to be the exact same I sub x prime centroid. So I can use that. The areas of my shapes are the exact same. Even that dy term that I used, even though it's not the same dy term I'm going to use, it's the same as the centroid term, right, from the last one. So I need that centroid term for each shape so that I can calculate the centroid, right? We had set up these tables where we had the area times the centroid of every shape. You multiply those two together, and then we can sum those to do our division of the centroid, right? Our centroid, in this case, we need to find y bar. So the sum of the y tilde a over sum of our areas. So I can use all of the information that I had in the last problem. I'm not finding anything new just yet. So my ay term, I'm going to have 9 million. For my rectangle, then another really big long number. For my void, and it is negative, so it gets subtracted out. And then 225,0,0,0,0. Right, just multiplying across a times y. So this times this gives me this. So now I just add down the columns, right? I do my summation. If I add my areas together, I get 64,828. Add my AYs together, I get 8,599,200. And then I plug each of these into my equation up here, all right, to find this centroid value. So my 8 times 10 to the 6th over that 64,828 number. Punch that into my calculator, and I get the y bar for this composite shape. I'm gonna delete just this part, because when I plug that into my calculator, it gave me 133. 133 millimeters. So my centroidal x-axis sits at this 133 millimeters. Right, so just under the centroids of my square and circle, and just above the centroid of the triangle. So now what I need to do is find the new dy value, right? We said that that dy value is the distance from the centroid of each shape to this centroidal axis. So in this case, it's going to be, for my square, let me make myself some room, create another table for myself. And I'm going to do the same table that we did in the first problem, but now my dy term is going to be that 133 minus the centroid of each shape. And then of course I have the a dy squared. So now for each of these, I need to find the distance to the centroid. So for my rectangle and my circle, it's going to be the same since they have the same centroid. So it's that 133 minus 150. But it's going to be the absolute value of that because this is just a distance. So 133 minus 150 gives me 17. dy just being the distance from the axis I'm finding the moment of inertia about, in this case, centroidal x-axis, to the distance of the centroid of the shape. So 17 for both the circle and the rectangle, and then for my triangle, it's 133 minus 100. So 33. And then again, I just do the multiplying across. I just do that multiplying across. I have 1.73 times 10 to the 7th. Then negative 17,672 times 17 squared gives me negative 5.11 times 10 to the 6th. And then my triangle gives me 2.45 times 10 to the 7th. And again, I just take the sum down the columns, right? I only need that first and last term for my moment of inertia. So exact same as the last problem, right? For this guy, 5.38 times 10 to the 8th. And now I need to plug in my calculator, summing down this column. I get 3.67 times 10 to the 7th. And then it's just adding these two terms together. Gives me my moment of inertia of the, of my centroidal x-axis, right? So that's the x prime. It's going to be those two added together, which now is 5.74 times 10 to the 8th millimeters to the 4th. Right, so I have a different moment of inertia now that I'm taking it about a different axis. So the key with these is figuring out your dy, knowing which axis you're taking it about. It's most often either going to be x or y axis or the centroidal x or y axis, which sometimes might even be the same thing. But it does make a difference where you take this moment of inertia. So pay attention to that dy term and understand where that's coming from and how you need to pull that out. So for our last and very final example for this class, we're going to find the moment of inertia about the x and y axis for this cross-sectional area of this beam that we're given. So this is an I-beam, and we want to calculate the moment of inertia for it. It gives us an x and a y axis here. And so we're going to use our parallel axis theorem and break our composite body here into basic shapes, make our table, and then solve for our moments of inertia. So again, we have to use parallel axis theorem here. Right, our moment of inertia about the x-axis is the centroidal moment of inertia plus a dy squared. And about the y-axis, it's our y centroidal moment of inertia, a dx squared. If we look at our shapes here, we see that we're given on the top, we have this long rectangle. It has a height of 1 inch and a length of 7 inches. And that is a fully shaded in shape. And then our next is that center part, the long vertical part. Has a distance of 6 inches and a width of 1 inch. And then we'll see that our bottom shape actually mirrors our top shape exactly. So it's another one that is 1 by 7. Now, don't actually have to do both of these shapes. We can do just one and multiply it twice over because of the symmetry of this, right? It's exactly symmetrical about the X and Y axis. This thing is totally symmetrical any way that you flip it around the axes. So we don't necessarily have to put both of these shapes in our table. We could just add a 2 multiplier to it if we wanted to. But if you want, you can also leave it as the 2 separate shapes to make sure that you're capturing everything in your table. Right, so what are the ingredients we need in our table here? We have 2 equations to solve now. So we've got a lot more stuff we're going to pack into this table. I'm actually going to put shape a little bit farther over. Move you. My shape, we'll call this guy 1, 2, and 3. Right, even though 1 and 3 are the same, I'm still going to put both of them in my table just to keep my mind straight. Right, so what else do I need in my table? I need my X centroidal, my Y centroidal that I pull from my tables, area, which is going to be the same for both equations, so that's handy. My area, my dx term, my dy term, and then I need a dx squared, and finally a dy squared. All of those to plug into my formula, right? That's my complete table for both of these. You can do 2 separate tables if you want to, or you can do 1 table. It's really up to you what makes the most sense in your brain. Again, you don't have to use tables at all if you don't want to. This is just, for me, the easiest way to organize the information. So I'm going to go and I'm going to look up my moment of inertia tables for rectangles, which again, we've seen a few times now. We know that for X, it's 1/12 base height cubed. And then for Y, it's 1/12 height base cubed. So whichever term is cubed is flipped. So in this case, I'll go ahead and make a little note of it, right? It's 1/12 base height cubed. In this case, it's 1/12 height base cubed. So for my rectangles here, this in maybe blue. For my rectangles, my horizontal ones are going to be 1/12 times 7 times 1 cubed, so 7/12, 0.583 is what I get in a calculator. And again, everything I get for number 1 is going to be exactly the same for number 3. And then for my vertical one, I have 1/12 times 1 times 6 cubed, which is 18. Now flip it and reverse it. We have 1/12 times 1 times 7 cubed. Gives me 28.583. Mirrored exactly to my 3. And then I plug in for my vertical guy, shape number 2 is 1/12 times 6 times 1 cubed, 0.5, right? Just pulling the numbers from my shapes into the equations that I pulled from my table, putting that all into my calculator. Next, I'll do my areas, and these are really easy since I only have heights and bases of 1, right? So my 7 times 1 is going to be 7, here exactly on the 3, and then 6 times 1 is 6. So now I need to find my centroid distances for all of them, and we'll notice if I look back at my diagram here, all of my X centroids for every shape falls right on the y-axis. So as it turns out, there is no distance between where the centroid is and the axis that I'm taking it about, right? When I do this dx term, there's no distance here, right? It just doesn't exist. It's always 0. It's on the y-axis. So my dx for all of these is going to be 0. And we'll notice if we look at this for my y's, I have my 6 by 1 guy has the same centroid as what I'm given, so he's going to be a 0. But my y distance is different for these top and these bottom ones, right? There is actually a distance between the centroid and the x-axis here. So there is a dy for my top and bottom girders. And again, they're exactly the same, right? So this distance here tells us is 3 inches, plus it's halfway through the inch down here. So that's going to be 3.5 inches. 3.5 is my dy in either direction. Again, I'm doing absolute value. I'm just doing distance to the centroid itself. I'm not doing positive or negative there. Then I have my area. So my area times dx squared. So now I'm just taking everything that I filled in my table. Area times dx, which all of my dx's are 0. So here I get zilch across the board. Then I do my area times my dy squared. And now, other than for my shape 2, which is 0, I will have some numbers. So 7 times 3.5 squared is 85.75. Exact same top and bottom. So this means that I need to add down my columns now to get my values that I need to plug into my moment of inertia equations. So adding my x's and my y's just down this column, get my sums. I have 19.17. My y centroidal moment of inertia is 57.67. And then finally my a dx squared, my a dy squared gives me 0, of course, and then 171.5. So now I can take all of these and plug these into those equations at the top. So I get 19.17 plus 171.5 for my x moment of inertia. For my y moment of inertia, I get 57.67 plus 0. So for my final answers, I'm going to get my x moment of inertia is 190.67 inches to the 4th, right? We've been working in inches this whole time. And my y moment of inertia is just that 57.67 inches to the 4th. And those are my final answers.